this is the way I think of physics, right? I'm an experimentalist, which means to me I'm an explorer. I'm happy to
Yeah.
listen to the theories, and they can give you some guidance about maybe where to go look next for something. But in the end, it's the going looking that I really care about.
Hello, this is Robinson Earhart here with the introduction to Robinson's podcast number 181. And this episode is with Jon Butterworth, who is professor of physics in the Department of Physics and Astronomy at University College London, where he works on the ATLAS experiment, a very cool name for an experiment, at the Large Hadron Collider near Geneva, Switzerland. And in this episode, Jon teaches me all about the Large Hadron Collider, which, sociologically speaking, didn't work at all the way that I had thought it did. And then we talk about the standard model of particle physics, how it connects to quantum field theory, before moving on to the Higgs boson and the search for the same. So Jon's book on the subject is called Most Wanted Particle, The Inside Story of the Hunt for the Higgs, the Heart of the Future of Physics. And you can find the link to that in the description. Reviews, comments, likes, all of these things are always appreciated. And there is now a Patreon for ad-free listening, show notes, and transcripts. And I will also apologize for Pins, who was a bit of a beast in the last few minutes of the episode, but by now most of you are used to that occasionally. And one last thing. So since I'm taking over some of the editing duties now, I'm wondering if you video watchers, whether on Spotify or YouTube, enjoy this format that I think I will be trying in this episode, though I haven't edited it yet, where it's picture in picture and the larger picture, well, both pictures, I suppose, are alternating depending on who's speaking. And I much prefer this to the side-by-side view because it's more dynamic and you can see the whole frame of the speaker. And I like that you can still see both people, which I don't like when it just switches from one camera to the other. So let me know in the comments what your thoughts are on this, since it will, if there's an outsized response in one direction or the other, that might influence the way that I do the editing going forward. But now, without any further ado, I hope you enjoyed this conversation as much as I enjoyed having it with Jon. Just to give you a little debriefing as we begin, the bulk of the physics that has been discussed on the show so far has been, I'd say, on the one hand, on the interpretations of quantum mechanics, and then on the other hand, string theory and quantum gravity and black holes and this sort of thing. So the standard model of particle physics itself hasn't really been explicitly addressed at all. But before we get into it, I wanted to ask how you first got into it. How you first got into the standard model.
Okay. So it depends how far to go back. I mean, I think there are two things as a kid that got me into doing, I guess, research and physics as the main thing. Do you want to go back that far?
Yeah, let's go.
Okay, so I remember when I was I guess about 10 years old. My brother is a few years younger than me, and with a friend, we decided we'd write a book on the whole of space, everything in space, right? I think we mainly meant the solar system at the time. We didn't really know the difference, but we started doing it. And if I got my dates right and my memory serves correctly, then it was, I think, Voyager was up there. So we made a contents page with all the planets and all the moons. And while we were doing it, like every week, we were having to add more moons. And of course, we gave up. It was one of those kid projects. We never wrote a word of it apart from the content page, I don't think. But the idea that there was stuff that no one knew and you couldn't find in books was and it was being added to, was my first feeling that I want to do that. I want to be the first person to find out a new thing about nature, and the thrill of the fact that the sum of human knowledge was growing, and maybe I could contribute to that, was really that stayed with me from that moment. It was that excitement of knowing that all the books were wrong, because today this thing found a new moon around Jupiter or whatever it was, and I can't even remember the moon. I'm not that interested in moons, but this idea of new information coming in, and research, the idea of what research was, really sunk in. And that was before I wasn't particularly physics or anything. It was just that, to me, is almost more important than what you research is the fact that you're finding something new out about the way the universe works, and I thought that was great. And then a bit later on, when I was doing maths, my maths A level, which in England is a thing you do kind of it was O level, which dates me in England anyway. But it's kind of you do when you're 15, 16 years old, high school stuff. And my maths teacher was teaching us how to differentiate, and we were measuring lines on curves and taking the gradient. And he said, so kind of secretly at the back, he said, if we're doing x squared, and if you make it 2x, it's always 2x. The answer for the gradient of x squared is always 2x. Just a simple bit of differentiation, which I know is not that simple maybe, but it wasn't that simple when we were 16 for sure. But and then the idea I got from that was that somehow maths was a kind of cheat sheet to the way the universe worked. And I think physics is really bringing the maths and that research idea together, and that's really where my love of particle physics, if you like, came in. And in a way, the Standard Model and the maths that lay behind the postulation of the Higgs boson is that ad absurdum almost, and yet the connection with reality, that you build an experiment, you go and look, you don't just think about it and do the maths, you go and connect it to the way the universe really behaves, is also and find out is also really important. So those two things were what set me on the path, if you like. And then I don't know how the rest of it. I wasn't always like fixated on research or particle physics, but those things stayed with me through all my student days and things. And then much later on, I was already doing a PhD in particle physics, and I did my PhD was working on an experiment in Hamburg, which was called Zeus, and it was going to collide electrons and protons together and study the internal structure of the proton. But one of the things, and I was working on the technical side of like building the event selection and the electronics and things that would help this thing work, which is fine. Programming is kind of my technical skill, I guess, that I contribute to particle physics. And as an aside, I did a study of beyond the Standard Model ideas, some new physics, a leptoquark it was, or a supersymmetric particle actually that looked like a leptoquark. And I wrote a little simulation for that and blah, blah. And of course we didn't find it. It was kind of a fun thing to look for, but we didn't actually find it. And so when I started doing a postdoc after that, I thought, well, I've had enough of studying things that aren't there. I want to go measure what's actually there. I want to go do Standard Model measurements. And that's where I kind of got into my research career. It was mostly been measuring the prediction, what the Standard Model, measuring things and comparing to the predictions of the Standard Model. And that's the much later step, if you like. That's why I'm not a beyond the Standard Model theorist. That's why I'm an experimentalist looking at measuring things and measuring the Standard Model at some level.
When you talk about this book that you planned on writing, it reminds me of Stephen Wolfram and these books that he would write as a youngster. And you could have been on that prodigious path had you kept at it. But then this interest you had in discovery at a young age is an apt tale to tell, because it foreshadows your role that you mentioned with Atlas and making a serious empirical discovery of the Higgs boson. We'll get to that in a few minutes. And then one other thing you said that stuck out at me is this idea of math as a cheat sheet to the universe, and as it's called in the philosophical literature, the unreasonable effectiveness of mathematics in physics is a question that I'm quite interested in. But okay, now getting back to some questions. Two things. One, you mentioned that your work involves testing the predictions of the standard model. So first, I think we should talk about what the standard model is quite broadly, and then second, you also mentioned that you studied the collision of protons and electrons in the Zeus experiment.
Yeah,
And collisions play a tremendous role in the empirical exploration of particle physics. And I don't think it's obvious why that is to the layperson, why collisions are so important. So first, what is the standard model, just roughly, and why are collisions so important for studying it?
sure. So the standard model is essentially it's a body of knowledge, a body of theory that encapsulates what we. I guess it's the answer we have at the moment. So imagine starting with any piece of material, asking yourself this question, which people have done, some strange types of people in the past. If you start with any material and you break it in half, and you break it in half again, and you break it in half again, and so on, how take the Zeno's paradox or whatever, go keep chopping it as far as much. The question is, does that process ever stop? Do you reach an indivisible component of nature? And if so, or does it just carry on forever? And if so, if you do you stop in the same place wherever you started from? Okay, so the bottom line is, are there a certain set of fundamental, if you like, indivisible constituents of nature? And of course, we've had ideas about this, about, the atom was first postulated as an indivisible constituent of nature. We know now that it's not indivisible, but still a reasonable good model for a lot of physics, a lot of science, a lot of nature. And the particle physics is really just pushing that envelope as far as you can, if you like. Are there fundamental constituents of nature? And if so, what are they? And if so, what are the forces between them, and how do they then combine to build the world around us? And the standard model, in a nutshell, is our best answer currently to that. Okay, that's what it is. It lays out what are the fundamental constituents of nature, what are the fundamental forces, how do they behave, and how does that lead to, the electron is one of the fundamental. It's a fundamental player in the standard model. It's one of the fundamental constituents of nature, and the quarks inside protons and neutrons are also fundamental players. And then the force of electromagnetism, which is carried by photons, which are quanta of light. All of these things are players in the standard model, and the standard model is essentially a mathematical formula in the end that lays out how these things relate to each other and how they therefore interact and how you predict what they're going to do next and explain the world around us. And it's incredibly successful at doing that.
Before I continue to probe this, I just want to get back to the Zeno's paradox that you mentioned at the beginning, and this is a bit orthogonal to where we're going, but some of the discussions I've had on the foundations of physics on this show, and particularly quantum gravity, we've talked about whether or not space is ultimately discrete or continuous. So causal set theory, for instance, the fundamental constituents of reality are space-time atoms, and space is discrete. And since you're in the business of cutting things in half forever and getting smaller and smaller, I'm wondering if you have a particularly strong opinion on the matter about whether or not these things will ultimately continue breaking down. But I guess this question is distinct from whether or not space itself is continuous.
Yeah, it seems so. I think what we do know is that things look very different when you get small enough, and when you get to very high energies as well. And we can talk in a minute, if you like, about how those are essentially the same thing in a sense. But that's actually one of the conceits in the map of the invisible. Actually, as you go far east, you go small, and you go up in energy. And
right.
So I think what we know is, as you do that, the world changes. So it doesn't make sense to think of things as particles in the same way we think of grains of sand or discrete objects like that. You're in the world of quantum field theory, and the people that you've been talking to who deal with string theory and quantum gravity and stuff are struggling with the fact that quantum field theory is what we need to describe the standard model, and it can encapsulate infinitely small particles once you introduce things like the Higgs. It has a mathematically consistent picture that describes nature and is okay. Is okay with infinitely small discrete particles. So that Zeno's paradox doesn't carry on forever in the standard model. In classical theories, it would carry on forever. And the problem is that general relativity, which describes gravity, which is not accommodated within the standard model, is a classical theory. So in classical theory, space is continuous and you can divide it forever. In the standard model, energy and force and particles are not continuous. They break down. They become quantized at some point and become quantum field theory. And that's a problem we have in physics, right? We don't know the resolution, and the people you've been talking to have been struggling with that. It's a long way from, at the moment, from having empirical evidence that will allow us to make sense of that, unfortunately. Although you can always hope for a better experiment. But my opinion is that in the end, and it is just an opinion, no, it's not based on evidence. My opinion is that that probably the quantum picture is closer to that in the end, gravity will have to roll over and become quantized. And I think most scientists probably think that too. Most who have an opinion, that's probably their opinion. But we don't know, to be honest. And general relativity is an absolutely beautiful theory that describes a vast array of stuff. But in the end, it probably has to give way to some kind of quantum version where the classical version of general relativity that we see in nature is a lower energy approximation of an underlying theory. So it's just an opinion, but that's where I think in the end, nature becomes quantized, probably. Which means the paradox stops, right? You can't divide the quantum up anymore.
And then returning to your comment about energy and size, perhaps in our macroscopic world, we think of energy increasing with size. So maybe the potential energy of a boulder hovering a foot above the ground is greater than a pebble at the same altitude. But this isn't the case with the microscopic or with waves. I think of radio waves and X-rays. X-rays are much more energetic.
And it's about how the energy is shared out. So when you make a boulder bigger, then you've got more energy because you've got more matter, but you're sharing it out over more and more matter. So the energy per proton or per atom in that boulder isn't growing. You're just adding more atoms which have energy. So it's more about energy density. It's about concentration at a point. And with a collider, in the quantum world, there's a relationship between energy and wavelength. So there's the de Broglie wavelength that's associated with any particle is the inverse of the momentum. So if you go to high momentum, which is like going to high energy, then you're going to a shorter wavelength. And the key, as you alluded to, with electromagnetic waves, is of course, if you want to see something really small, you need to probe it with a wavelength that is at least as small as the thing you're trying to see. Otherwise, it'll just be invisible or blurred out. So if you want to see the smallest things in nature, you need the shortest wavelengths. And if you want to get a short de Broglie wavelength, you need super high momentum. And that's why we need these big colliders, basically, because they're the highest momentum particles we can get in a lab. And then when we collide those beams together, we are probing nature with a shorter wavelength than we've never been able to do before. And therefore, we can see the smallest stuff in the universe. We can see the quarks and the leptons and maybe things inside them if there were things inside them. And empirically, so far, there's no sign of anything inside them. They look infinitely small, but obviously, it's always a working model. You build a better experiment, you might get more data that contradicts it.
You mentioned a few minutes ago that the standard model of particle physics is couched in quantum field theory. And one last sort of conceptual question I want to ask before we move more toward introducing the search for the Higgs boson is just what the relationship is between the standard model and quantum theory as it was formulated by like the 1920s or so? Because when we hear about things like the interpretations of quantum mechanics, like I already mentioned, none of this comes into it. We're not talking about the Higgs boson or gravity or anything like that. So I'm just wondering what the relationship is between the two.
So one of the relationships is that when quantum theory initially, I mean, it's the theory you need to describe subatomic physics, and that means, really fundamentally to describe electrons and photons is probably the first thing you hit. So why do atoms emit light and absorb light with particular frequencies and things like this? And that it's the kind of the Bohr atom. It's the fact that there are only certain discrete allowed orbits or bound states in an atom. And that just forced people into this idea of a theory that's kind of probabilistic, and you start talking about wave functions and things. That was then taken together with relativity, really, by Paul. So that was the theory of Heisenberg and Schrödinger, I guess. And I'm not a historian, so I'm probably going to get some of this wrong, but this is the way physicists, the way it looks when you're doing an undergraduate physics degree, maybe, or a PhD. But that was the kind of world of Schrödinger and Heisenberg, loosely speaking. And then you bring that together with Dirac brought that together with special relativity, actually. And this is one of the, I don't know if anyone's talked about this on here before. This is one of the moments in physics when you're learning physics, and you think, this is amazing. And it really happened. Dirac was trying to write down the equivalent of Schrödinger's equation, but rather than using the Newtonian relationship between energy and momentum and starting from there, he started from Einstein's relation in special relativity, so E equals mc squared, essentially, and tried to make it, basically had to get rid of the square. If you tried to make that a quantum mechanical equation, you ended up with negative energy particles. And of course, negative energy states, everything would just fall down into the lowest energy state, and the universe would be unstable. So that had to be wrong. So he said that's because it's a first order equation. It has a square root. It's really this simple. It has a square root, and with a square root, you get a plus or minus, and the minus is a big problem. He said, right, I have to make this a first order equation. And to do that, you have to pull in some really weird algebra where A times B doesn't equal B times A, because otherwise the equations don't work. He kind of forced it. It feels like, you think of the logic, it feels like you're forcing a square peg into a round hole. You're really, contorting your logic. Anyway, he came out with the Dirac equation, which did two things. I mean, it worked for a start. It brought relativity and quantum mechanics together. But it also explained what the spin of an electron was, which was we knew about but was puzzling people. This is kind of in the 30s and 40s, 30s, I think. And then it predicted the existence of antimatter as well, which no one had even observed, and it just seemed ludicrous. And within a few years, they actually found the antiparticle of the electron. And I know it sounds like I've digressed a little bit there, but this led to this formulation of quantum field theory, where you have the possibility. So it's grown out of the Schrödinger's equation or Heisenberg's uncertainty principle, all the stuff of the early quantum mechanics. They're still good. They still work for a lot of things. But you get this quantum field theory where you have the possibility of creation and annihilation of particles, because you've got matter and antimatter in there as well. And then I guess that was then the bedrock on which Feynman and Schwinger and Tominaga built quantum electrodynamics, which is the first kind of complete quantum field theory. So there's a clear progression from this. And all of that still is dealing essentially with electrons and photons. And then to get to the standard model, it's basically taking what Feynman and mainly Feynman's language is what we use, but it was independently developed by Tominaga and Schwinger. And it's taking that language and extending it not to just understand electromagnetism, but also the weak interaction and the strong interaction. And that becomes a standard model. And then at that point, you realize you have a problem with mass, and then you have to bring in the Higgs boson there as well. So the language that they're all discussed in is basically the same language as quantum electrodynamics, which came from Feynman, came from Dirac, came from Schrödinger and Heisenberg. So there's a clear path through in the maths, and there's things that are similar throughout them all. And the standard model is really then saying, okay, but there are more particles than just electrons and photons, and this is how you build a theory that includes the strong interaction and the weak interaction, as well as electromagnetism, and then allows those particles to have mass in a way that works.
Perfect. Thank you. That's great. Okay. And I think then now we are ready to move to the experiment. So first, what is the ATLAS experiment at the CERN Large Hadron Collider?
So the ATLAS experiment is probably the quickest way to grasp what it's for is that it's the highest resolution, highest bandwidth digital camera that we know how to build, and it's designed to photograph what happens when these protons collide at the Large Hadron Collider. And we go to a lot of effort to make these protons collide at the highest energies we've ever had. So when they collide, we want to know as much about the results of that collision as we possibly can. And that's what ATLAS is there to do. And I should say, also CMS, our friendly rivals, diametrically opposite on the ring. They're what we call general purpose detectors, designed to just see what happens when these protons collide, basically. And they're sort of cylindrical structures that surround the beam, and the two beams and the protons collide. To be honest, most of the protons miss, right? But some of them collide in the middle. The rest go around and have another go. And these cylinders, the beam goes through the kind of axis of the cylinder. They collide in the center of the cylinder, ideally. And there are kind of concentric cylinders of different technologies then around that. So there's a silicon pixel and tracking detectors that will record the path when a charged particle goes through. They're semiconductors in general. So the semiconductor is almost ready to conduct electricity, but a very small perturbation, such as the passage of a subatomic particle with some charge, will move an electron from the insulation band to the conduction band, and then carry electrical current, which you can read out and then tell that the particle went by. And there's a magnetic field around that, which bends the particles according to the momentum. So if you can join the dots on a track of the passage of a particle, then you can measure the curvature and you can measure its momentum. And then around that, there are calorimeters, which measure energy, as you would guess from the name, I guess, which are designed to essentially stop everything. And as it stops, it decelerates and it gives off photons. And if you're smart enough in the way you count the photons, then you can work out the energy of the particle that you stopped. And then around that, there's the most obvious thing. If you look at a picture of one of these detectors, the most obvious thing is always the muon system. It's only designed for one particle. It's the biggest bit of the detector. It's the outer layer, and it's the biggest bit. It's designed to detect this one fairly rare particle, the muon. It's like an electron, only heavier. It's they're produced in cosmic rays, but they're not very stable. So often they're a sign that something interesting happened in the collision. And because they're like the electron but heavier, they don't get stopped by the calorimeters because they're too heavy to be decelerated by hitting the electrons in the material, and they don't interact with the strong interaction, so they don't get stopped by the nuclei much either. So they kind of punch all the way through, but they're charged, so you can measure them on the outside of the detector as well. So that's basically what they do. And that covers basically all the standard model particles except for neutrinos, which you can't measure at all. That you can measure them if you have billions of them in a huge detector, and there are other experiments that do that.
Right.
But if you create one in a collision, your chances of seeing it essentially zero. So we can kind of deduce that they were probably there by the fact that the energy doesn't balance up, the momentum doesn't balance up transverse to the beam. So that's why they're cylinders; they completely surround the beam. So, yeah, so that's what they do. And coupled to that, of course, is a whole bunch of very fast readout electronics to try it, because we have 40 million bunch crossings a second. So 40 million bunches of protons per second, every 25 nanoseconds, passing through each other. And in each one of those is of order 100 proton-proton collisions. So we've got 4,000 megahertz-ish of proton collisions, coming at a 40 megahertz rate with a lot of data, many gigabytes per collision of data. So doing a data reduction job on that and trying to weed out the rubbish as quickly as you can and keep the things you care about is, there's basically an office block full of electronics next door to it trying to do that as well. And then it gets, the data gets farmed out all over the world on the computing grid, and it ends up on my laptop, basically.
Okay, there are a lot of questions there, a lot of thoughts. One thing that just comes to mind is that neutrinos are quite interesting, have a fascinating history, but you mentioned how hard they are to detect.
Yeah.
I think there are like billions or trillions of them passing through us, each of us, from the sun at any given moment, which is just pretty amazing. And they hardly ever interact with us. They build these huge, obviously, as you know, heavy water containers deep in mines to detect them. And it still happens pretty rarely.
Yeah, that's right. No, they're amazing. There's the kind of famous picture of a guy in a rowing boat going around the Super Kamiokande detector in Japan, which is built underground to do this. And the next big experiment in the US actually is going to create a neutrino beam and fire it to South Dakota from Illinois. It's called the June experiment, and it's going to be pretty cool. And they will be able to measure some small fraction of those neutrinos in that beam. But with Atlas, we have no chance.
And then continuing to talk for a minute about detectability, you mentioned that the muons are heavier than electrons.
Mm-hmm.
They're unstable. They don't interact with the strong force. Maybe this again just presages some of the things we might talk about when we get to the Higgs boson. But how do these features, so weight or mass, instability, interaction, how do all of these relate to detectability more generally?
Sure. So, first of all, the lifetime, the fact that they're unstable doesn't really matter to Atlas because they live long enough to travel hundreds of meters. So from our point of view, they're essentially stable. I mentioned that they're not stable. It's relevant that they're not stable because we don't see them in nature. We don't see them appearing in atoms. I mean, we see them produced in the upper atmosphere when a high energy particle hits the upper atmosphere from space. But they don't live very long. So they're not like electrons you find in everyday material. You don't find muons in everyday material for that reason. It doesn't really affect their detectability from our point of view. The detectability comes about, first of all, they have electric charge, which is a good thing for detecting them. And that means they show up they will show up in our silicon detectors and things. The fact that they're heavy and don't feel the strong force have two different effects. So you got to think of the calorimeter as it's atoms, it's dense material because it's designed to slow things down, to stop things. But essentially, an atom is a bunch of candy floss surrounded by a kernel, a bullet, or something. It's let's say a steel ball bearing surrounded by candy floss. Now, the candy floss is the light electrons, and the ball bearing is a really heavy nucleus in the middle. And the nucleus interacts via the strong force. It experiences the strong force. The candy floss only feels the electromagnetic force. When an electron hits that, it's only the size of a grain of sugar, so it will interact with the candy floss and be stopped by the candy floss. When a muon comes in, it's more like a bullet. It's because it's heavy, and it just punches straight through the candy floss. It doesn't care about the candy floss. There are other heavy particles called hadrons, pions mainly, that will do the same, except that they also feel a strong force, so they have got more chance of hitting the ball bearing in the middle as well because they're interacting by the strong force. The muon doesn't have that, so it won't stop. Basically, it will just punch all the way through. If it's really unlucky, it might hit one of the ball bearings, but very, very rarely because it's not feeling the strong force. So it will just bang right through. But if it bangs right through the calorimeter, then it will emerge on the other side, and it's still got electric charge. So we measure the path of it on the outside as well, and we never stop it. We never stop the muons, but we can at least we can measure their trajectory and their momentum. And if they get through the calorimeter, then they pretty much must be a muon because that's the only thing it would do. It would do that.
Two last things I wanted to get to just with the Large Hadron Collider, and one is you mentioned CMS,
Yeah.
your friendly rival, and the Large Hadron Collider and CERN in general. The Large Hadron Collider is a physical object. CERN is a group of people,
Mhm.
but they're both respectively huge. You mentioned that CMS is on the other side of this many kilometer long collider. Just how does the Large Hadron Collider work on a sociological level? I mean, you have thousands of people working on it. There are multiple experiments going on, different groups. Just I don't think I certainly don't understand how it all works exactly.
I guess the key concept is the collaboration. So each of these big detectors is run by a collaboration of thousands of physicists from dozens of countries, and different universities and things around around the world. So it's not like I go out there with my PhD students and postdocs and do an experiment and bring the data home. It's that we built some of this thing in London, and other people built other bits of it all around the world. We take it all to Geneva, we put it all together, it all works together, and we all get all the data from it all the time. So it's a very collaborative enterprise in that sense. All the data from everyone's bit of Atlas is shared, even though Atlas was built by different people all over the world and coordinated at CERN, obviously, to make sure it all functions properly and works, which is by no small challenge. It's a super high-tech jigsaw that has to all fit together perfectly. And then, so Atlas is run by a collaboration of literally 3,000 people. If you look at our papers, it's got 3,000 people on the author list of every paper. And the reason for that, I mean, I must admit there are papers out there that I haven't read that have got my name on. And that's because I made significant contributions to the experiment, and so, and I'm therefore a member of the collaboration. And it's not a perfect system actually, but it's better than if we didn't do that, we don't even put them. They're all alphabetically as well, so no one gets any individual priority or anything, which confuses the hell out of university administrators and everyone else. But it's the only way we can think of being sure that it'll work, because we don't want these rivalries to take over and split the collaborations. So, clearly there are a lot of egos and rivalries involved, and everyone's got to get their career, make their own career, and get recognized for the work they do somehow. So I'm not saying it's a solved problem, but the reason there are such big author lists is because it takes all those people to make the damn thing work, and then you really have to. You don't want to spend. There's enough work to do making it work, collecting the data, analyzing the data, making sure the results are right and publishing them, without spending another equal amount of time arguing about who actually goes on the author list and in what order. So we don't do that. But CMS is a separate collaboration. So in a way, it's scientifically, it's a guard. First of all, that each experiment's made different technology choices, so it's risk mitigation. That if one of them had made a bad choice, then the other one hopefully would still work, and the LHC would not be firing away with no detectors working. So that luckily they both did work, but they do both have different strengths and weaknesses in some places. Also helps you avoid groupthink at some level. You have some people over there keeping you honest, and may come up with some fancy idea that you hadn't thought of, and there's a room for innovation and the stimulation of innovation in that, I think, which is beneficial. But to be honest, right, Atlas has got a huge if you look at the map, Atlas is near the main laboratory. CMS is 15 kilometers away in the French countryside. So in the end, the social interactions mostly happen on the main lab in restaurant 1 or 2 on the CERN lab, and you try and there's a lot of gossip there, and people really do. I mean, it's friendly rivalry, okay. When we were on the verge of discovering the Higgs, people were pretty tight-lipped, I have to say. And you got to remember there are married couples on either side of the experiment.
Oh, really?
Either side of this divide as well. But everyone was pretty discreet on the whole at that point. It's usually quite a healthy relationship. And also, early career scientists in particular will quite often, do a studentship on one experiment, then move to another one for a postdoc and move back and so forth. So it's not a huge divide. But there's real different technology and different social norms in the two experiments, if you like, and different scientific norms to some extent in the two experiments, and it kind of works in that way.
Hmm. Well, now without any further ado, turning to some of the content that you cover in Most Wanted Particle, though, doesn't the book have a different title in the UK?
Yeah, it's called Smashing Physics in the UK, but I think that was too colloquial for the US publisher.
Yeah, you have a couple books with different titles in the US and the UK, which I found interesting. I guess I've heard that was a thing, that the publishers like having
Yeah,
different names, but it's kind of funny.
the two, actually, both of them are published by different people in the UK, but the US publisher, called The Experiment, they know their stuff. I prefer Smashing Physics, but as a title, but I can buy their argument that maybe it doesn't work as well for their market. And I must admit, this one, this Map of the Invisible, that's the UK version, but in the US version, it's called Atomland, and I like it. I prefer the American one actually because, and the way I don't have a copy here unfortunately, but it's produced like parchment, and it looks like it's kind of what I had in my head, because I see it as an explorer's map of subatomic physics, or a bit like the maps at the beginning of the maps of Middle Earth in Lord of the Rings or something. It was that kind of thing was in my head, and the American edition is kind of truer to that vision, which I couldn't really explain, and they got it somehow. It was great.
Yeah, no, I looked at Atomland as well, and I saw the cover, and the cover looks exactly like that. I really liked it.
Yeah, I love it. And the guy, I don't know, the guy who drew those maps, based on lots of conversations with me, is the guy who did who did the illustrations. Do you know Philip Pullman, his Dark Materials?
Yeah. Oh, yes.
He's called Chris Wormel, and he does the kind of woodcut style illustrations, at least for the later Philip Pullman books. That so I was very lucky that my UK publisher found him, and he's the perfect guy to draw those maps.
Yeah, I am a big fantasy fan, and I write a lot of fantasy too. So I've made plenty of maps, and I love making maps, and I love looking at maps. So so I love the cover.
Me too. And I also find, I don't know if maybe this is not the right time to talk about it, but this is the way I think of physics, right? I'm an experimentalist, which means to me I'm an explorer. I'm happy to listen to the theories, and they can give you some guidance about maybe where to go look next for something. But in the end, it's the going looking that I really care about, and I found that really interesting. Really, that analogy is really actually true to the way I think of my job. That's what I do. I'm a researcher, and I think of it as being an exploration, and so the maps are really very apt for that. I also, there was another reason I liked it actually. I used to write a blog. I still write a blog very occasionally, but I used to write a blog for the Guardian newspaper in the UK, and I discovered from the kind of blog style of writing, that you can explain some really quite complicated concepts if you put enough effort and time in, and if your readership is engaged and really wants to listen. But then people have a real problem working out how they all relate to each other. So any individual post might understand a thing, but they've not. But then I realized what I had as a physicist was essentially a map of where all these things sit, all these different concepts sit in the understanding of physics. And I thought then also the map idea comes to the fore again then, because you learn a little new, a little nugget of interest about physics, about a Higgs or about an electron or about a neutrino, but you don't have an overall picture of the standard model or of physics in general. You don't have anywhere to put that information. And I realize what I'm doing is I'm basically zooming in on bits of this map and explaining them, and I have the map in my head. So maybe I should try and give people an idea of what the map is, and that's partly what the book's for as well.
I like the idea of things like cosmic strings maybe being like little serpents in the sea of a medieval map or something like that.
Yeah. All right, so here be dragons, or maybe not. We have to go and look and see.
Well, before we get to the empirical discovery of the Higgs boson, I'd like to start with the theory.
Okay.
Just how was it found theoretically?
Right. So this dates back to the 60s, before I was born, never mind before I was a physicist. And it's to do with this idea, again, back to this, the divisibility of matter. And can you build a theory that will accommodate infinitely small particles? Because in principle, that means infinities are uncomfortable in nature, right? So an infinitely small particle means infinite energy density on the face of it, because it has some energy. And if it's just, it sounds like a black hole, right? It sounds terrible.
Yeah.
So how do you build a theory like that? And as the maths of this was developed, and again back to QED, actually, quantum electrodynamics, it was there's a property called renormalizability, which is a way of removing these infinities, but it only works if the theory is based on symmetry. Symmetry is called gauge symmetries technically, but it doesn't really matter. The point is, there's a mathematical principle which is actually very beautiful and elegant that says symmetries in nature lead to forces. In the same way, there's actually Noether's theorem that some of your listeners may have heard of, where there's a relationship between conserved quantities and global symmetries. There's also a relationship between local symmetries and the forces of the standard model, and it's a generalization of that, actually, which Feynman and others came up with. So that was a neat trick, but it doesn't allow the force-carrying particles to have mass. So as soon as you introduce a mass term, it breaks that symmetry. So that was a problem that people were wrestling with in the 60s. And actually, they thought, and I got told this by Peter Higgs, actually, because I wrote something wrong in the New Scientist, and he said, that's a great article, but they were not even thinking about the standard model, really. They were in the end, the Higgs mainly applied to W and Z bosons, which you can come to later. But they were thinking of particles called pions, which are not even fundamental particles. But it was nevertheless, they were trying to think in the abstract, because it seemed relevant. How would you build a theory with massive force carriers? And they couldn't do it, and it looked like they would need to at some point. And there's a neat trick which condensed matter physicists had already used, called spontaneous symmetry breaking, where you have a theory that's completely symmetric, but the ground state, the lowest energy state, is not. So you can. This is why people talk about wine bottles sometimes with the Higgs. So this shape at the bottom, the Mexican hat thing as well. Sometimes the shape of the bottom of a wine bottle with a lump in the middle. If you imagine a marble in the wine bottle and you shake it up and it's got lots of kinetic energy, it can be anywhere in the bottle. It's completely symmetric. The whole thing is symmetric around the middle of the bottle. But if you stand it on the table and let it settle, it will go off to one side, and then the ground state, when it stopped moving, is no longer symmetric. It's broken the symmetry by moving off. So that was the trick they were hoping would work, right? You could keep the gauge symmetries, which makes the infinities go away, and you could have massive particles because the ground state was asymmetric and had this spontaneous symmetry breaking. And that works in condensed matter, but it doesn't work relativistically, and it doesn't work when you. The problem with it is it produces a bunch of massless particles called Goldstone bosons, which just don't exist in nature. So this was the block that they were dealing with in the 60s, and what Higgs and Broughton Englert, who were working independently in Belgium, also noticed was that in the presence of another gauge theory, and in this case, they were looking at when you have spontaneous symmetry breaking and the gauge theory together, they look like two separate problems, but they actually solve each other. So they worked out that if you have a gauge theory there with massless particles and you have a spontaneous symmetry breaking going on at the same time, then they interact with each other such that the massless particles that were the Goldstone bosons become the extra bits of the other particles that you need in order to give them mass. And it all kind of works out very nicely. And what it boils down to, right, is that the mass of the particles, all the fundamental particles, is not a property they have intrinsically of themselves. They're something they have by interacting with this new field, which we call the Brout-Englert Higgs field, if you like. And it's the interactions with that give them mass. The particles themselves, in the absence of that field, would be massless. But that field is everywhere because it's like the nature has a spontaneously broken symmetry. It's what we call a vacuum expectation value, which is like the displacement of the marble from the middle of the bottle. It's not zero. It's not in the middle of the bottle. It's displaced. And that displacement is the equivalent of saying that there's this new energy field filling the universe. And by interacting with that, that's how particles get mass. So to bring that home, so that was kind of sitting there as a necessary ingredient of the Standard Model, and it turned out to be needed to be, as the data accumulated through the 60s, 70s, 80s, 90s, became more and more obvious that this thing had to be out there somewhere, or else everything we were thinking of was wrong. And coming back to the kind of empirical nature of this, you think, how would you detect whether this is right? I mean, you've basically invented this whole new field, filled the whole universe with it, which is great for a theorist, if you like. But and you've done it essentially just to make sure the maths works out okay. But can you get some empirical evidence this is right? How would you know this field is there in the universe, right? And the best analogy with that is, how would you know there's air in the room, right? So there's the room I'm in, there's air in this room. You can tell it's there because when I'm speaking to you, I'm making waves in it. I'm making pressure waves, which is sound waves, and I go into the microphone, and then technology takes over. If there was no air in the room, there's no background field, pressure field, if you like, in the room, then you wouldn't be able to hear that. And that's a very good analogy for what we're doing at the Large Hadron Collider. So if this background energy field, this background quantum field, is present in the universe, then if you hit it hard enough, you can make a wave in it. And because it's a quantum field, that wave is a quantum particle, basically. It's an excitation in that quantum field. That's the Higgs boson. So that's why we were so keen to discover it. It's not really that, we've discovered another particle. Very good. It's the fact that this is the evidence that that background energy field is there in the universe, and that is what gives particles mass. And so that was the kind of breakthrough that we were looking for. And it took a long time, should we say.
Well, a couple of things. First, you mentioned Higgs' correction to your article, I think, and
yeah.
He also had just worth mentioning, a very positive comment and blurb on your book.
He did. So. No, he was a big fan of the book in the end, I think. It was really nice. And he's not very he doesn't communicate a great deal these days. He doesn't do email. He doesn't answer the phone. So I was really pleased that he'd read the book even, and to get a positive comment from him was just fantastic.
And then, so bosons are, at least colloquially with us lay people, thought of as force-carrying particles.
Yep.
So I wonder why the Higgs mechanism is not thought of as a fifth force.
Yeah, it's a good question. And in some ways, it is. I mean, it's an interaction between particles, which is what we think of as a force. The difference is, well, the two differences. First of all, boson, actually, what it means is something that has an integer angular momentum. And the force carriers in general have a unit of one in some units, and the Higgs has 0. So they are different in that sense.
I see.
But the reason we don't think of it as a force is because the forces of the Standard Model are based on symmetries, as I was saying before. They're based on symmetry groups that you then you apply this gauge principle to, and that gives you the force carrier. The Higgs arises through a completely different route. So the mass of the Higgs in the Standard Model is completely different from the mass of the other forces, and the physics is different because it's not based on a symmetry. The Higgs is kind of added ad hoc with no symmetry behind it, really, whereas the other three arise from symmetries. So in some ways, it's sort of semantic. I mean, the Higgs can be exchanged between particles just like a photon can, so why not call it a force? And fair enough. But there is a reason behind the difference, and it's because of this thing. Some of them are arising from what we call gauge symmetries, and the Higgs boson is not. It's just added on almost ad hoc to explain mass at the end as a separate thing. And as a result of that, doesn't actually have any spin even, and there's other differences associated with it.
Yeah, is the Higgs particle the unique boson with integer zero spin?
Yeah, as far as certainly in the standard model, yes, and as far as we know in nature as well, yes.
Is there
Sorry,
some
the unique fundamental one. There are combinations of quarks and things that can have spin zero
right?
as well, but as a fundamental one, yeah, that's unique.
Is there some particular significance to its spin being zero for the mechanism?
Yeah. If it had a direction, then you would break Lorentz invariance. So you'd
Okay.
pick out it's everywhere in the universe. Remember, so you would then break the Lorentz symmetry of the universe, which underlies special relativity and the standard model. So yeah, that would be a big problem if it had a spin.
Mm-hmm.
So it really had to be scalar. Otherwise you have a favored direction in nature that is picked out by the spin of the Higgs.
And then you said we'd come to bosons later, which we did. But what is the precise connection between the Higgs boson and then the Higgs field?
So the Higgs boson is essentially an excitation in the Higgs field. So back to my analogy of pressure and sound, the Higgs field is the air in the room, and the Higgs boson is a sound wave. So it's
Okay.
or if you prefer closer analogy, an electromagnetic field in a room, and the Higgs will be the photon, which is an excitation in that field.
And I know that there was a famous book about the Higgs particle that called it the God particle.
Yeah.
But is there a good reason for referring to it as the God? I'm not a particularly theological reason for referring to it as the God particle, but is it of such significance that it is worth calling the God particle, at least for dramatic purposes?
I mean, no, it's my correct. It's my actual honest answer, but I can see why. It was Leon Lederman, I think, who did that, and I haven't read the book, so I don't know the details. But back then, when it was something that you needed in order to make sense of the standard model, and you had no evidence for whether it existed or not, I can see an analogy with people's lives there, where you think, how do we make sense of the universe? We postulate the existence of God. We haven't got any evidence that it's there or not. But if it's not there, nothing works. And at some level, maybe there's an analogy there with the Higgs, because that is the role it played in the standard model. This whole business of the standard model, it was constructed as a self-consistent quantum field theory, but it required the existence of a Higgs boson, which no one had any evidence for. Okay, no direct evidence for until now. So until 2014 or whatever, 2013. So I think I can see where it was coming from. I must admit I don't like the analogy, and given that we now have irrefutable evidence that the Higgs boson exists, which I think we're unlikely to get for God, then it's even less appropriate than it was when Lederman wrote it down. But that's probably where it's coming from. So in the sense that you needed it to make sense of a lot of other stuff. Some people need God to do that, I guess, and that was the analogy they were drawing on.
And speaking of analogies, keeping in mind some of our listeners for whom the more accurate microscopic level description of how the Higgs field and boson work, if it might have been over their head, which is entirely possible, I'm wondering if you have a macroscopic analogy for how we can think of the Higgs boson as working. Something I've heard in the past is that we can kind of think of it as the field producing a drag on objects that pass through it, and that gives them mass. But I'm wondering if anything comes to mind for you.
Yeah, I know what comes to mind. So when the they were arguing in the UK about whether we would actually fund the Large Hadron Collider, which is while I was still working in Hamburg. But the minister at the time put out a competition with exactly that question. So can you explain it? I've got a degree in, I don't know, probably politics and philosophy and economics. Can you explain it to me? What this Higgs is for and why you care? And a colleague, a senior colleague of mine at UCL actually came up with the winner of this competition, got a bottle of champagne out of it to explain to the minister. It's a guy called David Miller, who's retired now, but it's a really great analogy, I think, and it's still the best one I can think of as well. So imagine, this is Margaret Thatcher, by the way, was I don't know the average age of your listeners, but she was a prime minister in the 80s when I was growing up as a kid. And she was the prime minister at the time, I think, as well. Oh, no, not quite. No, it was John Major by then. But anyway, digressing. Imagine a cocktail party. And someone comes in the room who's not famous at all and tries to get to the bar. And it's really quite easy to get to the bar because no one cares who they are and they just cut through and they get to the bar. Then imagine Margaret Thatcher coming into the room and all the politicians want to hack her. They all want to talk to her, and it becomes incredibly hard for her to move around. And if she's going in one direction, she can maybe keep going in that direction, but it's really hard to change direction. And that's the Higgs field is all the Tory politicians hanging around with their cocktails, and the particle that has mass is Margaret Thatcher, and the particle that has no mass is the one that just no one has heard of and gets straight through to the bar. So that's the Higgs mechanism in cocktail party land. And you can even get the Higgs boson out of that as well, because then you imagine someone peeks their head round. Thatcher's not there yet. Someone peeks their head round the door and says, "She's on her way," and then this little knot of gossipers forms and says, "Yeah, she's on her way. She's on her way. What do you say?" And this blob of higher density people kind of moves around the room as well, and that's an excitation in the cocktail party background, which is the Higgs boson moving through as well. See what I mean?
So obviously, this analogy.
Too much British politics involved in.
Yeah, no. Is the blob of people one boson, or is each person a boson?
No. The blob is one boson. The boson is the excitation. So the wave, if you like, the wave of density of people going through the room, if you like.
Yeah. And the bigger the blob, then the more excited the boson, maybe.
Yeah, that's right.
Okay, perfect. And so we can easily grasp the role that the Higgs boson plays in everyday life, since it gives my cat mass, for instance. But on a much larger scale, is it supposed to have played any particularly important roles in cosmology, for instance, say with inflation or in other areas?
Yeah, so, well, first of all, I have to say most of your cat's mass is not from the Higgs boson.
Oh, really?
Yeah, it's so the most of the mass in an atom comes from the nucleus, and most of the mass of the nucleus actually comes from the strong force. So it's only the mass of the fundamental particles that come from the Higgs. So your cat would not be a cat if it wasn't for the Higgs. So it's still important, don't get me wrong. But because the electrons all get their mass from the Higgs. So, and if the electrons didn't have mass, then atoms wouldn't hold together. So it's still vital. Don't worry, I'm not. But it's interesting that most of the mass of the cat is actually in the protons and neutrons, and that's coming from the strong force.
Okay. I need this is a good clarification. But the quarks get their mass from the strong force.
No,
I'm not sorry. The quarks get their mass from the Higgs boson.
Yeah.
And then the quarks then are held together by the strong force.
Yeah. But that has a lot of binding energy. So
the strong force, because it has energy, it adds mass.
Yeah, basically that's right. Yeah.
Okay. So that's a really great, important clarification. I'm glad.
Yeah. So, and then you asked about cosmology. So, I mean, there are a couple of things there. One is, yes, there will have been some phase transition in the universe which is the equivalent of the wine bottle, the marble in the wine bottle, cooling down. As the universe cools down, this symmetry gets broken. So in the very early universe, this broken symmetry that gives things mass, that means that the Higgs field is everywhere. That's not the case in the early universe. There's so much energy that we're not in the ground state, so the symmetry is not broken, so everything's massless effectively. And at some point, as the universe cools, we go through a phase transition where the W boson, the Z boson, all the electron and so on acquire their mass. That's very, very early on in the universe, and I'm not sure how much. I mean, it has to have happened, otherwise the universe wouldn't happen, but I don't think it's had much influence on the structure of the universe as we see it in terms of the cosmological measurements that people make from things like the James Webb Telescope or whatever at the moment. So the other connection that may be there is a bit more tenuous and speculative. Is that you mentioned inflation? Inflation is also probably driven by a scalar boson, like the Higgs, and there may be, and you asked earlier, is it the only one in nature? Well, it's the only fundamental one in the Standard Model, but dark energy and inflation may also be due to something like this as well. And there are models where they are due to scalar bosons. We don't know whether that's true. We don't know whether they're there. They're certainly not present in the Standard Model, but they may be present in nature. So one of the kind of more speculative but interesting and not completely disconnected from observation and pragmatism is one of the areas of particle physics and cosmology is exploring whether there are really links between that. Now that we know there really is at least one fundamental scalar boson in the universe, maybe it's connected with these other puzzles. There isn't a compelling, neatly done up theory that joins them up, but there are various ideas around about how they might connect.
I'd like to go back to my cat for a moment.
Yeah.
Not just because I find my cat interesting.
You're very handsome.
Thank you. Thank you. But I'm curious now about where the mass in the cat comes from. So the fundamental particles that make her up get their mass from the Higgs boson.
Yeah.
Most of the mass, you said, comes from the strong force. Now, is there also mass in the cat coming from, say, like the electromagnetic interactions in her brain, the very, very weak gravitational force that is also sort of binding her towards her center of mass? Are all of these interactions adding additional mass to the cat?
They all at some level contribute, because in the end, mass and energy are the same thing. So anything which is, they're different forms of the same thing. So E equals mc squared, basically. So anything that the binding energy of the electrons around the protons also contributes positively or negatively to the mass of the cat. Any kinetic energy, any form of energy that the cat has will be contributing to the mass. Yeah. So. Yeah, so no, that's what's. I mean, the way you can, I think of it with the protons and the neutrons, for instance, is you have three quarks, which if their free mass, their mass they get from the Higgs is a tiny fraction of the mass of the proton, but they're confined to a tiny space by the strong force, and because of that, they're vibrating very, very rapidly within that space, because their momentum has to be very uncertain, because their position. In terms of quantum mechanics, right? What we're saying is their wavelength has to be really small, because they're in this small place. That means their energy has to be really high, and it's that energy that is giving the mass to the proton, basically, via E equals mc squared. So if you think back to what I was saying about what we were both discussing, wavelength and energy, and how they're inversely related. So small wavelength means high energy. The proton is really quite small. So to fit anything into that, then its wavelength has to be really quite small. And that means its energy has to be high. And therefore, by E equals mc squared, or if you like, m equals E over c squared, there's a mass term coming in there. And that's where most of the cat mass comes from. But that's true of any interaction. The strong interaction is particularly strong, as the name suggests. So that is by far the biggest contribution. But any kind of interaction in terms of the forces or gravity or electromagnetism will also have similar kinds of impacts on the mass. They'll just be a lot smaller. The strong interaction is what dominates.
This is obviously not news to you, but it is fascinating to me just how much reality diverges from our folk intuitions. And this is just one great example of it, where for thousands of, probably since the beginning of humankind, at the most basic level, we've probably thought mass is just a function of volume and density. But it is really not this. I mean, that plays some role,
Yeah, yeah.
but that's not fundamentally where mass comes from at all.
The issue is, and this again, this is the map thing, right? The issue is once you go below the atomic scale, intuition is really a poor guide. once you
Mm-hmm.
once you're in the world where quantum mechanics is relevant, our intuition has evolved over the lifetime of the species to be incredibly good at incredibly good guide to things we meet in everyday life. But once you get inside the atom, it's not applicable very often. And right back to what you said at the beginning, it's unreasonable somehow that mathematics is that we've developed along with our intuition about how to catch a tennis ball or how not to fall over when we're running downstairs or whatever, all of which require huge amounts of intuition about classical physics at some level. We've also managed to develop in parallel mathematics, which turns out to be a really good guide for what's going on inside the atom, which is amazing.
Mm. But before we return back to CERN and the Large Hadron Collider, I have one question about physics beyond the Standard Model and the Higgs Boson.
Mhm.
And I'm wondering whether, because I've never heard this before, so I must be wrong with my intuition somewhere, whether the Higgs Boson is at all central to efforts at unifying gravity and quantum mechanics, since the Higgs Boson is what gives fundamental particles mass
Mm-hmm.
in the Standard Model, and gravity, at least at our macroscopic level, is very much connected to mass.
Yeah, but no, I mean the answer is no. Actually, really, it's not really that central, and that's because gravity itself doesn't really distinguish between energy and mass. So the fundamental object in general relativity is an energy momentum tensor, which has terms that are due to mass. But from a point of view, from a long way away, gravity doesn't care whether your energy is in the form of protons and neutrons or photons or whatever. So if they're over there, they're behaving like energy, and that's what distorts space time. That's what creates gravity. So it's not really. I mean, there were people before the LHC turned on. It's less of less interest now. I think because we found the Higgs. There were people trying to avoid the need for the Higgs by saying that actually gravity comes into play much earlier than we thought. There are extra dimensions of space time. I think you mentioned them before with neutrinos, but you could have had extra dimensions of space time that gravity is sensitive to, but which once you get to the energy of the LHC, you can actually probe. And these dimensions are present in string theory, but in string theory they're way out of reach of the collider. But if you brought them down to LHC energy, you could maybe get away without needing a Higgs at all. And people, for the various reasons, people didn't like the idea of there being this fundamental scalar. So these extra dimension models, which would have explained quantum gravity at some level, would have also been a way to avoid the need for a Higgs as well. But now we've found the Higgs, of course, that's a lot less interesting because we know it's there.
Mm-hmm.
I think it's not really central to quantum gravity investigations, at least at the moment. It's still, I mean, I have to say, on the timescale of physics, it's still an important new piece of information that people are still digesting. So I wouldn't want to bet too much money that it won't actually turn out to be important in that. But at the moment, I wouldn't say it's central to those investigations now.
Huh. Well, what you just said raises a new question for me. You said it's relatively new in the timescale of physics, but it doesn't seem relatively new in the timescale of quantum physics, in the sense that it's been theoretically around since the 60s, and a lot of people have been very certain that it's there.
Yep.
So in what sense is it new? Is it that the discovery a decade or so ago has resulted in more work empirically that needs to be done?
Yeah, it's
Or
sociologically interesting, actually, because you're absolutely right that a whole bunch of theorists have been assuming it was there for a long time. And the actual knowledge that it's really there has had a big impact on the field, even though you might have thought it wouldn't have done. And well, there are a couple of reasons for that. One is that, there's a certain kind of physicist who, when there's a real new phenomenon to get your teeth into, then you start doing more precise calculations of it and things, and that can throw up more insight. Another is that we didn't, although they kind of knew it was there, we didn't know what the mass was, and it turns out the actual knowledge of the mass is important and interesting, and might be on the cusp of whether, for instance, the universe is metastable or stable, and maybe that's telling us something interesting about how the universe evolved.
sorry, did you say metastable or matter stable?
Metastable.
Okay.
I mean, obviously, the universe has to be either nearly stable or completely stable, because otherwise it wouldn't be here anymore. So metastable just means that it's practically stable, but it, in principle, might not be in the very, very long run. And the Higgs mass is sitting somewhere, implying that it's right on the borderline between the two, actually, which is probably insight. There's probably an insight there if we could work out what it meant. So those are a couple of the reasons, and the other reason, maybe a more negative reason for it having an impact, is that a lot of theorists also thought supersymmetry or some other beyond the standard model idea would show up at the same time as the Higgs, and that just hasn't happened. So now people have to take the standard model a lot more seriously than they did in some ways. I mean, I think if you'd have asked theorists in, I don't know, 2008, 9, just before we turned on the LHC, what do you think will happen? I think most of them would said we will find the Higgs, but we will also find a lot of supersymmetric partners of the other particles as well. And we haven't. And we may still, they may be hiding somewhere a bit less obvious, but it's looking less and less likely. And that's had a huge sociological impact on the field in general, theory and experiment. And people are, there's still some diehards thinking there's still possibilities that supersymmetry will be there, but it's nowhere near as monolithically the overwhelming favored theory that it used to be. And certainly you have to take the idea that the standard model might be a very, very good effective theory on its own with no help from beyond the standard model for quite a range of energy. Right now, it seems to be that way. So all these things have subtly changed the way people look at theoretical physics, and I say that they're kind of 10 years is not. It's not that recent. It's not that long ago, but that's the discovery that did that, not the events in the 60s when the theories postulated it. When it was postulated, it was just one theory idea amongst a zillion others, right? It's only because that's the way nature behaves that it's become super interesting.
When you said metastable, you really got my attention. I was thinking, second order stability or abstract stability, but not. It's kind of less exciting, your metastability, but it does raise the interesting question to me about, or that sort of relates to the barber paradox. So who shaves the barber in the town where the barber shaves everybody who doesn't shave themselves? But the question is, what gives mass to the Higgs boson?
Oh, the Higgs does, though. That's okay. It's
okay.
The standard model within that is completely self-consistent, and it builds that in as well. This is the amazing thing, right? We've got this completely internally consistent theory now, which doesn't explain dark matter or dark energy or gravity, but within its own purview, it's completely self-consistent and doesn't need anything else to help it out. It's kind of amazing. Mm-hmm. The stability, just to be, maybe it's worth just saying another word about that. So we're saying, I talked about the wine bottle, and you've got the rim of the wine bottle, which is a local minimum where the marble will end up, and that's where the universe is now. And when we talk about whether it's metastable or stable, if that's really a global minimum and really the lowest point the marble can ever get to, then that makes it really stable. But if the wine, maybe it's better to go to the Mexican hat, so it's like that kind of thing instead. If the hat has got another lip down here with a lower vacuum, and we're in a kind of local minimum, but actually we could tunnel through to a different minimum, there's another global minimum somewhere else. That's what I mean by metastability, and it means the universe could at some point tunnel through to a different vacuum, a different minimum. But we know that whatever, if that happens, it has to be far enough away that the probability is so low that it hasn't happened in 13.8 billion years. So it's not going to affect our lives in any way. But from the point of view of how did the universe evolve and why is it the way it is, it might be a big clue as to what's actually going on. It's the other thing that the model for this is that why are sand dunes always got the same angle? Why do they always form at the same angle? That's because that's the cusp between stability and instability. The sand piles up until it falls down, and in the end, that leads you to one angle for a given kind of sand. And you always have the same slope of a sand dune, because if it was any steeper, it would fall down until it was that slope, and if it was any shallower, the sand would get piled up on it until it was steeper, and in the end, it settles at the point where it's just about stable. And it looks like maybe the universe did that at some point, and that may be a big insight into what's going on. The cat kept this stuff, you see.
Yes. The cat wants chicken. The cat's much more interested in chicken.
Oh dear.
But the last thing I wanted to talk about as we finish was a bit more about what life is like at the LHC or working on LHC data from afar.
Mm-hmm.
Because you mentioned that at the time, you, CMS, the other, well, maybe they were your main rivals in this case, but people were tight-lipped. There were spouses on opposite sides of the collider. What was or is daily work like at or adjacent to the LHC?
It's very varied depending on your role. So when the time that I spent most time actually at CERN was around 2000, between 2008 and 2012, and I was leading one of the analysis groups there, a couple of the analysis groups, and honestly, it was meetings, was what I was doing all the time, just getting people together to make decisions, to suggest ways forward, to suggest that wasn't the right way forward, to help decide who was going to actually write a paper on a thing that we just, so it was really that kind of stuff. Meetings about physics mostly. I mean, a lot of physics arguments, but the role I was in then, that's what I was doing. I was running meetings or going to meetings, and that was that. If you're a student there or a postdoc, probably a lot of what you're doing will be programming and data analysis. And I do that now at UCL. Now I'm not running meetings anymore, but that's something you can do remotely as well. I mean, I travel to CERN about once a month now, but I spend most of my time in London teaching and then analyzing data and writing papers. But there, you'll spend quite a lot of time in front of your desk, in front of your computer screen, trying to work out why that plot doesn't look right, and trying to work out what the uncertainties on it really are, and so on, and trying to work out why your plot is different from the other student's plot, this kind of stuff, and that carries on all the way through. And then that's the kind of data analysis side. But then these experiments take a lot of skill to run, and there are a lot of people working with engineers to build the things initially, and that was a lot of what we were doing when I joined in the noughties, the 2010s and the 20s. And we were building bits of it at UCL and then taking it out there and trying to test it with the other bits and trying to make sure it all integrated properly and that you could get the cooling, the heat out and the power in and the data out and all that stuff. Of course, it's now running, so the construction is no longer an issue, but it still takes a lot of monitoring and occasional repair and maintenance and intervention. So there's always people, when it's running, there's always people on shift sitting in the control room, monitoring the data that's coming in, looking for problems, starting it up, closing it down, going in, sending someone in to look at a bit of the detector that might have broken. If we can get in, we can't often get in to bits of it because when it's running, you can't get inside. So it's very varied what's going on. It depends what role you have in the experiment, and most people do more than one of these roles over the course of a career and over the course of an experiment as well. And some of those things you can do remotely. So I used to do data quality monitoring shifts from my office in London as well, because it's all online, and I'd just be looking at histograms and if there was a problem, then I'd report it at a meeting, and people would go and check what was going on. So it's that gives you a flavour of the variety of things that people are doing, I guess.
Mm-hmm.
And honestly, from my point of view, I don't really ever need to go and touch the experiment these days. But I need to go to CERN anyway, just to meet some people. You can do a lot remotely, but you do need to meet people occasionally, and it's hard to establish relationships remotely. It's good. It's easy to keep them going once they're established, but it's hard. It's very hard to actually build a team entirely remotely, I think. Still.
Right. Well, Jon, thank you so much for this. This has been so fun. I apologize for the meowing beast toward the
kind of
end of the episode.
Zorro didn't show up over this side, to be honest. But I shut the door so firmly, I guess you can't get in.
Yeah.
That was fun.